Good afternoon, ladies and gentlemen, and welcome to the webinar of LAMPAS on laser-based surface structuring for home appliance. Just a few words to explain what is LAMPAS. LAMPAS is an EU project, EU-founded project, which started in January 2019, and this year will go to the end. The mission of the EU project LAMPAS is to develop lasers, high-power laser with ultra-short pulses that, with a new concept of optical delivery system, is able to manufacturing on multi-scale topographies special features on the micro and nanometer range. Just to be much more concrete, we are speaking about surface features like hydrophobic surfaces, hydrophilic surfaces, micro-BOCDC surfaces, and so on. This is made through a high power, ultra short pulses laser of 1.5 kilowatts with the aim to have a high throughput processing, 1 to 5 square meter per minute. All this is supported by advanced process monitoring system, and all must be taking account the minimal workpiece heating, multiple scaled structure with very high resolution, and advanced surface function on very large area. There are several technological challenges that has been solved during these 4 years of project, and just to name the key partners of this project: Truth, Scanlab, Technische Universität Dresden, New Infrared Technology, Bosch, LASEA, BSH, EPIC, and University of Dresden again as a coordination of overall project. So let's say LAMPAS is bringing today a real solution for laser structuring of large surfaces. And this could be a big potential solution for surfaces normally used in home appliances. So here we are. Today we will speak about this specific solution for this topic. Here I stop talking and I will introduce first of all Raul Garcia from company Microreleus. Then we will have Johan Di Maio from company MANUTECH and Ander Villeit from BSH. We will close the meeting with discussion, and after all we can remain in the room for networking and further question or curiosity among us. So I stop sharing, and I really glad to introduce Raul Garcia from Microreleus. So Raul, the attention and the floor is yours. Okay, presentation mode.
Okay, can you see my screen? Can you hear me?
Yes, we can see your screen, but you have to go in presentation mode.
Yes, okay. Thank you very much, Antonio, for your presentation, for your introduction.
Okay.
I am Raul Garcia, and today I will speak about industrialization of functional and decorative laser using laser texturing. Okay. So I will speak just 1 minute about who we are and the technology and what we are doing for industries like home appliances using this texturing both for design and for functionalization. Okay, so we are a services provider for industry, so we are a workshop. What we do is industrial engraving, laser texturing, and laser microstructuring. Using lasers since 2013, nanosecond laser in 5-axis in this case, and in 2016 we added femtosecond laser in 5-axis, And this year, 2022, we are going to be pioneers with a bigger femtosecond laser machine in 5 axis to be able to engrave, texturize, and microstructure also big parts and heavy workpieces. So what a femtosecond laser is and what a nanosecond laser is. So depending on the kind of structure that we are going to engrave, we are going to use one technology or the other. So nanosecond laser is a short pulse duration laser. So there's some heat affected area. So we are going to have some burn. If what we are going to achieve, what we are interested in is to have some design texture, for example, imitation of carbon fiber, let's say wood, any other decorative texture, a nanosecond laser will be probably enough. On the other hand, well, if what we want to achieve is some functionality on the part, so microns become important, very good tolerances become important, sharp edges, very good superficial quality, and so on, then we have to go to femtosecond laser. In this case, it is an ultra short pulse duration laser. There's almost no thermal affection over the part, so we can engrave absolutely burr-free with a clean engraving, very sharp edges, and burr-free, as explained. So what can we do? The summary finally is that we can work in big parts or big, heavy, absolutely standard molds or tool over any 3D shape, engraving in a way that was not possible before. Engraving doing dozens of microns, details of those or structures of dozens of microns. So there are a lot of new possibilities here. In terms of design, we can engrave impressive textures for a high-end result part, or to avoid paint, coating from final part, etc. Everything engraved in the mold, so we are going to have the result just because of this plastic injection. We can achieve but functionality as well. So we can improve functionality thanks to the microstructure of the tool or of the part. Some possibilities are hydrophobicity, friction changes, antibacterial properties, reduction of scratches, lighting, anti-comfortating, soft touch, and so on. We are going to see here some examples of them. We can work over mold or over final part. We work a lot in micro reliefs, we work a lot on the mold, because of course you do the engraving once, and just because of the replication in the injection you have in all the parts. But sometimes we have to work also in final parts, series that require micromilling, like microfluidic devices, special lighting devices, prostheses, prototypes, and so on. In this specific example, we can see how we work. So from the initial data of having the grayscale or the design of the texture and the surface where we want to engrave this texture, that's the initial data. What we do is we map the 3D file of the mold in this case. So we create the tension lines of extension and compression that the texture needs to follow to adapt properly to this 3D shape. And then we adapt the texture over the mapping, creating a render. So that's the image of what we are going to achieve in the final part. So here we can see an example of Gianfranco Ferrer-Uomo, where we can see the mold insert texturized, in this case with nanosecond laser, and the plastic injected final part. So design possibilities are absolutely infinite. Whatever you're able to design, we can engrave it. That's a big, big difference compared with other technologies like chemical etching. Some other examples, here we can see a mold, injection of Sorlin, plastic, transparent Sorlin, tetins. In this case, the mold was not even with a parting line in the middle. It was just a cavity. And thanks to the 5 axes of the machine, we are able to engrave inside the cavity to achieve this nice product in the final injected part. Some other examples, again, this one was without parting line. It was a total cavity, degressive roughness density, imitation of whatever we want, for example, textile part. in this part here for the Nina Ricci perfume. We took the design from original textile part. And in this case, what we wanted to show is that we really have a lot of possibilities in terms of design. No limitation, this image is coming from an illustration. So we separate in different layers to have different effects from 3D engraving, the roughness density. We see the part here with a lot of grain, which is dying progressively and mixing with this progressive depth texture. Everything here is engraved using nanosecond laser, except the colors that are done using femtosecond laser. So these colors are because of a nano microstructure that we can create in the tool in the order of 1 micron that diffracts the light. So that's why we can see colors also in the injected part. Here we can see the tool where we can see the colors depending on how the light is going there, and the plastic injected part where we can see perfectly the colors as well. Some other examples in this case is decorative texture with a functional purpose that could be directly applied into home appliances as well to imitate brushed aluminum. In this case, this is of the Land Rover Defender, and in this case, the radar was placed behind the part. So there was no possibility of the part to be metal. It should be plastic because of the good behavior of the radar. That's why we analyzed with confocal microscope the brushed of the metal and imitated it and engraved the mold. And here we can see the final injected part that seems to be aluminum, but it is really plastic. Very applicable to home appliances in this case, this kind of texture. As we can see, very natural and organic behavior of the texture that seems to be real aluminum. Some other possibilities we have for anti-comfort tape, for example, is to have holograms. So we can have one logo, two logos, one logo and one image, etc. Just because of the movement of the part, because we can engrave such microstructure with kind of controlled polishing with the same laser, femtosecond laser in this case, to have this effect, to have two different images in the part, as we can see here. Very interesting for anti-copy and design as well. In terms of functionality, we can speak about hydrophobicity, for example. In this case, we see the comparison of the water drop after and before engraving the mold, the tool. So what we are doing is some kind of micro peaks in the range of 20 micron pitch and 20 micron depth. And these peaks, what are going to do is that the behavior of the water drop comes totally different. This black area in the middle was texturized from the mold, so this is injected, and the other part is not texturized. We can see that the behavior of the water drop is totally different on the area which is texturized and which is not. So this area becomes super hydrophobic. Some other effects. Velvet to have a really nice touch of a plastic part. Seems to be totally a different material, but it's really plastic just because of the microstructure we can create in the mold. Soft touch effect, or even reduce the effect of the scratches. So it is not like there is no scratches, but it is much more difficult to see them. With a specific project on that, comparing with some other technologies and achieving very good results in terms of anti-scratch surface. That's the example of the velvet. So everything that we can see here in black and in the injected part, we are going to have a really, really, really nice touch and nice effect in the final part. That's the example on the anti-scratch. How we comparing the roughness of the groove versus the texturing general roughness and the lightness. Okay, so in all the cases we see that the laser was much better than chemical etching in this case to reduce these scratches and have a kind of anti-scratch surface thanks to the engraving on the mold. Self-lubricating textures. Finally, any functionality that we can do in the range of, because of having a geometry of the range of dozens of microns, is possible to be done using this technology. Also in lighting, sometimes happened that the customer didn't have enough light in a screen. They didn't know why they were having a lot of losses, for example, here in a 90-degree part. So we can create a controlled microstructure all around here that makes the product much more efficient to have much more luminance in the final expected area. Like curtains even. So in this case, we can see a mold where we engraved everything, leaving microprisms up in the tool, so they will be inside plastic. And this is to have a light curtain effect, like screen LEDs coming from outside the part, from the bottom, and the structures on the top are bigger and deeper than the structures on the bottom to achieve this homogeneity all around the part. It's the same concept we used in the Cupra Tavascan concept for this light curtain effect, and that we can see here in this small video that even putting different parts, we can achieve different functionalities that could be indicators for different stuff. That's the quality we can live. So it's very close to polish. So that's why we can do a lot of things on lighting as well, totally applicable to home appliances also. And also in light diffusion. So to be able to delete or to avoid the hotspot of the LED, just of the micro roughness, micro texture controlled from the mold. So that's a little bit what I wanted to share. What we are offering with this technology, with femto, with nanosecond laser technology, is the service: laser microstructuring, laser texturing, and industrial engraving. Service focused on maximizing the added value of customer, applied on final part, on tool. A lot of customers pay us for R&D, for tests. We collaborate with technology centers, universities. Of course, we are a workshop, so sometimes if a customer wants to apply, for example, to work on, let's say, antibacterial for specific bacteria, whatever, we cannot develop here. So we collaborate with some technology centers, universities that can give us this knowledge and their experience. So that's everything from my side. I don't know if you have any doubt, want to discuss about everything. I'm here to try to help. Thank you so much.
Thank you so much, Raul. It's very impressive, and really you show, I think that today you had a little more time to show some example, and this is really fantastic.
Thank you.
I don't know if somebody has a question. Okay, maybe I make the first question. So I open, I break the ice. I think that your structuring is very complex, and you have to work with, let's say, several layers and processes. How you handle the design of this? I mean, the software is a quite complex topic, because somehow you should understand which could be the final results, having in the software also a lot of laser parameter or process parameter.
It's not so much complex, the software, because finally what we do is we buy the machine and we use the machine for customer. So the machine supplier has already good solution in terms of software. Okay, it could be more complex or less complex, but finally you learn to do everything. There are different ways to program this. So there are different softwares that we have to use. But the key point here is the parameters that we have to use in the machine, or which is the most appropriate way of programming on each project. And the difference here can be very, very, very important on doing on one way or the other, and you can be successful using one path or the other. And this is just possible with a lot of experience after having done a lot of different projects. That is when you really realize when a software is needed, or when such kind of parameters of way of programming is needed, or the other.
Yes, thank you. Very interesting. And I see Johan Di Maio from a company MANUTECH that raised hands. Please, what is your mind?
Hello, Raul.
Hello.
Thank you for this very interesting talk. You talked about molding,
Yeah.
and I was wondering, did you face any issues when transferring the nanostructures from the mold to the final piece? Because it is known that these structures are very small, and sometimes you lose the diffractive effect.
Yeah, diffractive effect is very specific case in the ones I showed before, because everything I showed, we were speaking in the range of dozens of microns. So a lot of textures were 200 microns, 300 microns, 100 micron. So for those kind of textures, we usually do not have a problem. We have a lot of data about that, and we're usually replicating between 80 and 97, 98% of the structures, okay? So in that case, it's okay. In the specific case of light diffraction, this is different because we are in the range of just 1 micron. So this is something that we cannot control, but we can force it to happen because of the affection of the laser on the part. And what we saw is that there is replication in the plastic part. You inject, no need of special injection, and you can see the effect in the part. But of course, there is no 100% of the structure. If you analyze with confocal microscope in the mold or in the plastic part, there is no 100% of replication. You always have more nanostructure in the mold than in the plastic part, but it's good enough to see this effect. And we didn't investigate a lot on that because all the projects that we have done on that area in the light diffraction were for R&D for customer. So they are the ones who investigate on this kind of texture, because one of the main limitations that you have with that is that are textures that are very easy to scratch, to damage, both in the tool and in the plastic part. So sometimes it's difficult for them to be interesting for a production. Okay, it should be something protected or very specific, and nowadays is the main limitation on that texture.
Yes, great. We have a question in the chat coming from Nazir Basha. Nazir, if you like, please show yourself and make directly the question. And also, this is also to the other people, show yourself. We are just 20, 30 friends here around. Nazir? You can activate the audio. Let's say maybe I do myself, but Nazir, then if you want also you can show yourself. So Nazir is asking, did you try texturing on glass to create super hydrophobic surfaces?
We never tried, but the behavior of our specific laser, which is infrared, so it's not the most appropriate one in glass. In glass, it's different than the behavior of in steel. So I would not be very optimistic. I'm not saying this is not possible to do, but I would not be very optimistic. Maybe there is people in the room that has more experience on that, but with our laser, we never tried before. We never had this request from customer.
Okay. I see also another question now from Abel Gil Villalba that yes. I don't see in the main screen, probably because he's not joining the full room, but okay, he's right. Hello, have you tried angle independent laser coloring, not based on light diffraction? Thanks.
We can do it, but not thanks to the microstructuring. So it's by oxidation. So this is something that if it's for final part is okay, but if it's for molding, makes no sense because plastic will copy nothing. I'm afraid that when you want some specific color, this is more in the nanotechnology range, that more that in the micro technology, that is the one that we work.
Okay, okay. So I don't see any other question. Maybe just a note. With my colleague, we will invite all the participants to join the main room. So you can join and show yourself and make the question. And now is also time to introduce again Joan Di Maio. He already made the question from company MANUTECH. Please, Johan, share your presentation and make your show your slides.
Is it working?
Yes, perfect. Go ahead.
Okay, so thank you for the kind introduction. So good afternoon, everyone. I am Joan Di Maio, Research and Development Engineer at MANUTECH USD. So I'm glad to have the opportunity to present our expertise in laser microprocessing, especially in the field of home appliances, which is the topic of today. So who are we? So I will start on a brief description of our organization, which is a little bit more complex than standard companies, but still probably makes our attractivity. For all of our productions, we are dedicated in laser femtosecond technologies. Such very specific lasers provide pulses of gigawatt peak powers during few hundreds of femtoseconds, as it was presented by our previous speaker. It gives the possibility of generating almost no heat effects by instantaneous sublimation of the matter on almost all kinds of materials. So to play with such high-value lasers, MANUTECH has the status of an economical interest group. So it means that we are driven by several academic and industrial entities, and the main ones are presented here. Our job is to provide feasibility studies with femtosecond solutions specifically, as well as developing proofs of concepts related to the developed processes. So this way, we are clearly linked to innovations coming from the academic world, and we try to promote them for future industrial applications. So that is why the economical environment of MANUTECH aims at being complementary. The research partners are more focused on low TRL, while industrial partners can concentrate on production of final solutions. And MANUTECH is in the middle of these two partners. So to do that, MANUTECH is equipped of 15 laser platforms. Most of them are composed of femtosecond lasers, ranging from few watts to almost 300 watts for very precise requirements and also for high-speed issues. Challenges such as high-dimensional patterning can be accessed by dedicated positioning stages that can provide almost 1 meter long travels. MANUTECH has several characterization systems that facilitate its reactivity for customers' requirements. One of them is called P2M for multi-scale, multifunctional platform and provides topography, wettability tests, and mechanical indentation measurements at once. This is also supported by a second system, a focused ion beam, coupled with a scanning electronic microscope, giving both highly resolved images and microstructural informations on a micrometric scale. So now let's talk about applications. So our main realizations are related to engraving and marking, cutting, and what I will more focus on, surface functionalization. The idea of this working field is to provide customized surface properties for specific uses such as improved adherence, modified friction, wettability changes, and so on. As told previously, one of the main strengths of femtosecond lasers is the ability to interact with all kinds of materials, from metals to biological films, from ceramics to polymers. Since laser technology is always matter sensitive, our main job is to define and optimize the laser and process parameters for each situation. Now let's focus on some home appliances applications. So here are some of the properties that MANUTECH has been working on with time. For instance, we can mention antibacterial properties for most devices, anti-limestone for devices that work with water at high temperatures, anti-icing for fridges, for instance, enhanced liquid flows, self-cleaning for pans and ovens, or for instance, food preservation with micro-drilled packages. This example described here aimed at improving cleaning durability of stainless steel grids by comparing the wetness with the textured samples. Here is the surface roughness, and which is quite similar to what Raoul presented before. We can see a cleaner surface after 7 weeks when these surfaces are textured. Another really studied application is the capacity of modifying liquid flows on surfaces to provide, for instance, self-cleaning behaviors. It would help reducing the use of chemicals as new environmental standards are more and more restrictive. The two pictures on the left compare non-textured aluminum with an hydrophobic femtosecond texturation. In the middle, you can see wettability tests on a super hydrophobic surface, also textured with a femtosecond laser. Very briefly, laser can, of course, be used as personalization tools thanks to an interaction spot as small as few tens of microns. This was applied here for cooking by customizing pans. Each sample was processed with a unique scanning field of almost 30 centimeters, which is not as easy as it seems. Anti-limestone was also conducted with the idea of proposing a mix of two interlaced textures. One texture that still accepts water for vaporizing efficiency issues, and one texture that is repellent for improving limestone chipping. So finally, here is an SEM panel of some of the femtosecond textures that were already developed for one or another application, which show the infinite possibilities of such a tool. So now I would like to finish my talk on a use case that goes a little bit deeper into the details, even if not really exactly correlated to home appliances targets. This gives me the opportunity to present the interaction that we can have with the scientists and the optimizing protocol that we generally conduct prior to future industrialization. So this use case is more related to medical applications, but since it deals with also antibacterial properties, it can be interesting for the main topic of this session as well. Complementary to antibacterial properties, conducted works also focus on bone cell repellence and adhesion. Key identified factors to provide such properties are first, the chemistry of the surface, second, the wettability properties that affect the protein adsorption, and as a consequence, the cell adhesion. And third, the type of roughness that can guide stem cells differentiation as well as repellence or adhesion. One of the main projects that drives these researches come from the Europe funding. So it is called Laser Implant and gathers 6 European partners on a total budget of almost 2 million euros during 2 years. It aims at designing surfaces with bone repellence and adhesion properties for respectively bone and dental implants. It is expected at the end of the project, a demonstrator that could provide femtosecond textures on these devices and with process characteristics adapted to the medical industry. On this slide, you can see 2 fluorescent confocal images with laser textured and mirror polished areas and revealing the density of the Streptococcus mutans bacteria that are mostly responsible for dental infections. We can here clearly see a major impact depending on the texture rugosity provided by femtosecond lasers. In the same manner, fibronectin proteins that are involved in the differentiation of stem cells, and particularly on bone cells forming, are also impacted by the surface texturing. For further information, we just published a paper in the Nanomaterials journal. And since we seem to be able to improve bone adhesion, we tried also to, in the context of this project, to find other types of texturing that could rather repel bone cells for easier imprint removal applications. Here you can see some multi-level textures that mix polished surfaces, laser-induced nanostructures, and rough impacts. We can easily see on the left-hand side video that cells are attracted by the brighter lines. The flower texture was specifically designed to force stem cells to spread into an equivalent shape. Indeed, it is known that this is one of the main reasons why these cells will differentiate into one or another type. Among the new promising properties of these surfaces, adaptations of the laser processes to industrial requirements are still at stake. Robustness regarding parameters variations, as well as processing time decrease, are two main topics that can limit an industrial integration. So here you can see, for instance, the evolution of the surface topography with laser repetition rate for the two previous textures. It can be clearly seen that one of the two textures is much more sensitive of thermal effects. So to compensate such issues, MANUTECH has the capacity of developing and testing dedicated strategies to maximize the performances of these femtosecond lasers, both hardware and software. The strategies presented here are currently being tested on implants in the context of the project. And to finish my presentation, I would like to point out the next challenges that femtosecond laser processing will be facing. Of course, and as told previously, speed upscaling is a major condition for industrial production. Several solutions exist with pros and cons, such as high-speed scanning systems or beam shaping, and LAMPAS already presented some of these examples. Linked to that, cost optimization is also important, since first investments in femtosecond solutions can be still expensive. And the analysis of the surface chemistry after ablation may be necessary, depending on the application, since it is known that they can be reactive during the first years following the surface modification. Also, new surfaces properties can be found when reducing the sizes of the features, and MANUTECH as just being equipped with a UV femtosecond laser for that. And finally, this could lead to new opportunities and yet undiscovered applications. So this is the end of my talk. I hope that I convinced you that femtosecond lasers are versatile tools that can drastically improve nowadays lives. We can finally notice that this technology also matches our worries of reducing our environmental impact by completely replacing chemical solutions. Thank you for your attention.
Thank you so much. I will start from your last sentence. I think that this is really a very important message to bring out, that photonics and laser technologies are also supporting our planet to be more green, because we can really reduce drastically the use of chemical stuff and other agents. So really, I really appreciate a lot, and I like a lot of your last slide. So where you put on the table the challenges. So now I challenge you. You put on the table 5 points from which you need more. So tell me where we have to start first. On these 5 challenges, what is the most important for you now?
I think it's quite difficult to give just one solution, because depending on the application, you may need one or another challenge to be solved. The 2 first points that I mentioned, I mean, speed upscaling and cost optimization, are quite linked. The problem of femtosecond lasers, and mainly lasers in general, is the size of the modified area. And the fact that we have to mark a complete shape point by point is quite long. So I think for an industrialization, the main problem is the speed of marking. And for that, we need higher repetition rate lasers. And if you have higher repetition rate lasers, you will have also higher mean powers. And if you have mean powers and you want also to rather increase more and more the speed of marking, you will need, for instance, beam shaping and multi-dot marking. And when you have these 2 points, you have the issues of energy handling about for the optics that you use. So we have to play with all of these elements. But I think, to my mind, the main challenge that we have to face right now for I would say simple applications with femtosecond lasers is the speed increase.
Okay. I would say that from this point of view, also, this is a great result of LAMPAS. Now we are speaking about kilowatt level ultra-fast laser. So I think that at least the first part has been solved. But I bring home the challenge that now we have to manage this power into the piece. So how we shape the beam and also how we manage the thermal impact on the parts. But okay. I see one question from Alain Abou Khalil. He raised the hands, and then there is also another one from the chat. But Khalil, please.
Hello, Johan. Hello, everybody. Thank you for this presentation. I have just a curious question for Johan. You mentioned making a demonstrator at the end of the project. So what do you think the challenges that you are facing to make a movable and transportable femtosecond laser machine with a scanner to do laser structuring on implants?
Right now, the objective of the project is not to have something that we can carry and transport everywhere. So we are still thinking of making a tabletop machine with an optical table, for instance. The main issue of making a demonstrator is taking care of the windings of the implants. Right now, we are not considering this complex shape, so we work as if we were on a cylindrical part. But I think that the next step, the next challenge that we will have to face dealing with this demonstrator is to take into account this winding shape.
And do you think they will have a big effect on the laser structuring, or you can just go through them without any problem?
This is a good question, and this is more related to the biological tests for which I'm not
Yes.
in the details.
Okay. Thank you very much.
Thank you.
Good presentation. Thank you.
Thank you.
Very interesting. I see that Nazir made also to you the question. Are you working or are you planning to work texturing glass?
So as I told in my presentation, we recently bought a UV femtosecond laser. And the two main applications that we want to work on is first the capacity on working on glass, both in terms of cutting and structuring, and also to be able to mark thinner, smaller features to be able to have new functionalities with, for instance, nanostructures that would have much less periodicity and, for instance, antibacterial properties.
Great.
So yes, we want to work on glasses.
Great. So I think that Nazir would be happy, and I recommend that anybody who would like to be in contact with Johan, with Raul, and later also with Anna, if you can chat during this meeting, or you can reach me by email, and I'm really happy to introduce any person to anybody else. Okay, I don't see any other question. Okay, we are more or less on time. So thank you so much, Johan. And now I'm really glad to introduce Ander Virlalte from company BSH. So I think that we can start sharing The slides.
Yes, so thanks, Antonio, for the introduction. So I'm through the mobile phone of Anna, so hopefully you can hear me quite well. So I have some technical difficulties. So yeah, so first of all, I will introduce myself. My name is Ander Villate. Been working for BSH for around 13 years now, and basically all these years related to laser topics. And at this moment, I'm a global technical leader for the development of digital decoration technologies, in which laser is playing a big role here. So if you can go to the next one, please. Yeah, so what about BSH? So what do we do? In general, we are producers of all kinds of big and small home appliances, the ones you can find everywhere. So from oven cooking, surface cooking, ventilation, cooling, dish care, laundry care, and small appliances. And for this, as an example, we have this purple small thing on the bottom. This is one of our latest devices, a Fresh App, which is basically a device that has a plasma generator that helps to reduce the odors on clothes. So it's a nice tool, nice gadget. Next one, please. About our brand, maybe if I say BSH, you do not know the company, but when we look to the brands, probably they are more familiar. So we have the general big brands like Bosch, Siemens, and Ness for Gaggenau. We have also the local brands, like in the case of Spain, where I'm located, it's Balay. We have our own ecosystem, which is Home Connect, which is the ecosystem that allows us to connect all our appliances together. And then we have the different service brands. As an example, we have the company called WeWash, in which we are basically having one company which is able to share laundry care between different people without having to buy each one a washing machine. Next one, please. Yeah, about the company itself. So we are #1 producer in Europe for home appliances. We are around about 60,000 employees worldwide with 40 production sites. Turnover is over 15 billion euros, and we reinvest around 5% of our net income in research and development. Then next one, we can already start talking about LAMPAS. So basically, we are participating in LAMPAS in the specs definition and the application development. So we have been contributing with different use cases and requirements with a clear focus on a productive environment. So for us, it's very important that everything that comes out from LAMPAS has a landing place on our factories. And as mentioned, our interest is quite clear. So we want to obtain different functional surfaces on metal parts in line, but also in a controlled way. Next, please. Yeah, so our expectation and vision, again here, so we want to have a robust industry-oriented prototype which is able to functionalize these metal surfaces in a cycle time compatible with series production lines. So now we all know we can obtain functional surfaces on metal parts, but for us, for example, you need to imagine that the takt time of factory would be more or less of around 30 seconds. So everything that we do about 30 seconds in a line will be a problem. And of course, with these functional properties, we want to increase the value of our products. Next, please. So what are the applications we are working in LAMPAS? So we have anti-finger properties, new decoration finishes, easy to clean properties, and antibacterial properties. And today I want to give you a couple of examples about the easy to clean properties. Of course, we cannot go a lot in the detail, but I think it would be quite interesting to hear these two cases. Next, please. And next. So we have these two applications. So the first one is easy to clean properties for cooking appliances. And the second one is not really an easy to clean property, but it's anti-calc on heating elements. Next one, please. So for the easy to clean properties on cooking appliances, so we have, for example, we have here 6 examples that we have analyzed. In this case, we were using the LEAP technology. And of course, we have not here all the laser parameters, But if we go to the next slide, please. So we have characterized all these different surfaces in our lab here. There is one example of an SEM image. Next one, please. And we have also studied the contact angle analysis. Of course, for us, when we are talking about cooking appliances, we want to increase as much as possible the contact angle with oil, for example. And when we start with the standard stainless steel, we are about 90 degrees with oil and about 80 degrees with water. You can see here that with the different properties we have obtained in LAMPAS, we can reach, depending on the surface, but we can reach up to 135 degrees with contact angle with oil, and more or less 150 degrees with water. Next, please. So here, this is a bit difficult to explain, but basically we have an internal procedure to evaluate the easy to clean properties. It consists of applying some kind of different food compositions on the surface, then burn them, and then have two cleaning steps, which are quite different one to the other. And with this, we can obtain more or less, by weighting the part, we can obtain how good the cleaning process is. So next, please. So if we look to the results of the 6 different textures I've shown before. So for example, with the LAMPAS 3, we can see that in the first cleaning step, we can reach up to almost 90% of cleaning. And after the second step, we are almost cleaning 96% of the soil. Compared to the standard stainless steel, which is 35% in the first step and 59% in the second step, we see already a big advantage of this. So it's a promising result. Of course, you can imagine that texturing with laser metal part will modify the aesthetical appearance of the part. But we have one use case in which we are also looking for this modification of the aesthetic of the stainless steel, so turning it into almost a black color. So this could be also a good opportunity to combine this aesthetic decoration plus the easy to clean properties. So next one, please. About the second use case, I don't have so much information, but here we are analyzing, as an example, a resistance which is covered in water. And here we are testing 4 different surface characteristics. And in this case, we are not using the lip process. We are using, let's say, a normal laser without the lip module. If we go to the next slide, please. So here we have some images. So we also measured here the perfilometry of the different areas. And next one, please. And it's a very short summary. What we can advance is that with some of the structures, we already see that there are some areas in which the detergent deposition or calc deposition is lower than with the standard steel, which is again also promising. And of course, there are a lot of challenges here because we need to take into account that there will be some corrosion issues probably in the future, but we will need to evaluate this. And next, please. And of course, all this work is thanks to all the participants in the LAMPAS project. And next one. So thanks for your attention. Sorry for the technical difficulties that I had. Hopefully, it was still understandable. And if there is any questions now, I will put on my headphones and I can hear them and try to answer through the mobile phone of Anna. So thanks a lot.
Thank you so much, Anders. And okay, don't worry, we heard you perfectly. And here I want also to thank my colleague Helena and Hannah that supported us during this technical issue. Johan, I see that you raised the hands. Please go ahead.
Yes, thank you very much for this presentation. So I have 2 questions. Maybe I missed one information during the presentation. So did you use the 1.5 kilowatt laser that Antonio was referring in the beginning of the presentation?
Not yet.
Not yet. Okay. And the second question is about the DLIP technology. So it refers to direct laser interference patterning, right?
Mm-hmm. Right.
And my question is, so it is very promising technology for large area texturing. My question is, what is the biggest area that you succeeded in marking with just one laser shot, without any translations?
Yeah. So this was done in a prototype at TUD. So it's not even with the intermediate LAMPAS machine. So
Okay.
probably the area was very, very small.
Okay.
But in any case, we will have this polygon scanner. So for us, having a translation of the part is not a big problem.
Okay. So, and to finish, sorry.
No, don't
No,
worry.
it's
Go ahead.
So the main issue of translating a DLIP shape is the recovering between each spot, because you have very straight lines, and if you want to translate your spots, you may have some issues when recovering these straight lines. Did you see such issues or not?
Yeah, as mentioned, not yet. Probably we will encounter this kind of issues, but
Okay.
not yet, because the final prototype of LAMPAS is still not put all together. But that's a good hint, and we are aware of that. Yes.
Okay. Thank you. I'm finished.
Thanks.
Okay, great. I see now Rahul.
Yeah, thanks. Thank you, Ander, for your very interesting presentation, and same for you, Joan, for your very interesting presentation as well. And I have, we work with translation movement, of course, Joan, like following your comment here, because of course, if we want to apply some pattern to a 3D big shape, we are doing it day after day. So our machine is it's 7 axes, so it's 5 mechanical axes. And once we are placed in a position, we work on a patch, okay? The size of this patch, of this area that we just move the 2 optical axes, it depends on the length that you are using and the defocalization that you are okay with it on each case, okay? Then it is true that the tolerance of the optical axis is different than the tolerance of the mechanical axis, and the border between patches can be seen. But the strategy here that we use, at least, is we remove in the order of half micron per laser layer, okay? So we do 1 complete layer, just half micron. Then we do a second complete layer, and the patches are never placed at the same place. It's random, okay? So that's how you can avoid the previous patches. And finally, the final result, it is very, very nice. And in a lot of cases, you are not able to see those patches. But of course, it is always something to take care, and it is always some kind of issue. Absolutely. That's my comment on that point, because we're working on that day after day in the molds or in parts.
Yeah, thank you. Anders, do you want to comment?
No, nothing else from my side, no.
No, okay. Okay, I see also another question from the chat from Geoff Shannon that I don't see. So, okay, today is the day of technical issue. He asked Geoff, have you completed any longevity testing on the functional surfaces? Do you know how long the surface continue to show functionality? That is a quite interesting question from and what we can.
Very interesting. So in the case of the metal parts, we have not, or at least inside LAMPAS, we have not completed long life tests. But I can speak, for example, in EMM technology. So with plastic parts, we have conducted like work tests to the mold and to the part. And in the case of the mold, we are surpassing like 100,000 shots, which is quite okay. And the properties were still there. And the lifetime of the parts, this depends a lot on the environment of the part. So, for example, in the case of the cooking appliances, we have some abrasion tests. That the question is very right. We will have some issues with the long life duration of the textures. So probably we will have to check this in the future. This is of course in the planning in LAMPAS, but there are some other parts like the heating elements that are not in contact with the user, which sometimes we are using quite abrasive products to clean. So the lifetime there we expect to be a bit longer.
Okay, great, great. No, really interesting this question. So I think that we have no other question from the room. Yeah, just a moment. No, I'm sorry, I'm wrong. Abel Gil Villalba. Thanks for the talk. Are you using a spatial light modulator or a physical element like prism to generate the beam interference? Here we are really going to the optical part. Anders, can you comment?
Cannot say anything here. Probably you, Jan, tell me you can say something better than me.
Yes, Abel is asking a very specific question. If in the project LAMPAS we are using a light modulator or some elements to generate the beam interference. I'm not really aware about which is the technology adopted. I don't know if Anders, if you can comment.
Neither me. No, I cannot help you this question. Sorry.
Okay, Abel, I will say I bring home this question, and if we keep in touch, I will come back with the answer from the expert, the optical expert of LAMPAS project. I see also a quite cryptic comment from Jose Antonio Ramos, DLIP, D-A-I-P. So this is a direct laser interference pattern, but I don't understand what is meaning Jose. Maybe you can, he's not in the main room, so we keep it as a cryptic. No, he's joining the room. Great, great. Jose. Switch on also the camera, and you can put your question directly. You are saying that is the answer to the previous question. Okay.
Yeah, but I think the main question was what is behind the DLIP?
Exactly.
ELIP. Yes.
So I just was answering the question. As is well known, from the public information, we are using direct laser interference patterning.
Yes, but the question is probably how we generate the pattern.
Oh, well, in combination with the polygonal scanner. We don't use any other modulator.
Okay.
Because the direct interference laser patterning needs to combine two beams that interfere at the focusing plane. And generally, either you have a static optical element, like a prism, that generates two beams coming from one beam, and then you recombine them at the focusing point. And at this position, you have the sample, and you will have both the sample and the interference patterning. And the second solution would be, instead of using a prism, you will use a modulator that can transform the beam from one beam to two or more beams. So you can have both solutions. And at LAMPAS, I don't know if you use one or the other. I think this is the question. But maybe this is not public yet.
No, it is public yet. We are using the interference by optics, standard refractive optics.
Okay, so here we are going to, I see a question from Senai Innovation. Okay, I see Tiago Pereira raise the hands. Okay, great.
That's it. Thank you. Can you hear me?
Yes, sir. Perfect.
Okay. So thank you, Antonio. Thank you for the presentation from Raul. Johan and Ander, very interesting. I have a general question. A few years ago, we used to see these applications using picosecond, and today we mainly hear femtosecond. Is it the case that picosecond is losing a little bit of place, or is there any real application for picosecond? Is there a case of energy or power?
If I can start a simple answer, I think this is not a matter of the femtosecond is replacing the picosecond. I think both lasers are have different kind of applications in today. I don't think that we have more femtoseconds now and picosecond previously. I think they are both on the market now. It really depends, I think, on the kind of application you have. Maybe femtosecond lasers will have more, even more peak powers than picosecond lasers, and maybe you can interact easier with more complex materials with probably a little bit less thermal effects. But for most applications, you can also find some picoseconds if you use them correctly.
Yes.
If you allow me to add just a couple of concepts also, in particular to the LAMPAS project, we need to use a picosecond for optical reasons, given the coherence length that makes easier to make interferencing with pico than with femto. And then I think mostly with metal is reported an increase on ablation rates of around 10 times in case of femto regarding to pico. But of course, it's also to have in consideration with the average powers and quality, etc.
Thank you.
Yes, sure. Okay. So I don't see any other question raising. Maybe I try just to wrap up this very interesting meeting. I would say my feeling, my opinion is really that we are not speaking about potential application. Here we are really going into real application. So I have really clear in mind the example shown by Rahul from Rico Releus. They are machining molds used in production. So now, I remember when I started the university, laser was a solution looking for a problem. Here, I think that there is only one problem from where we start, because we have really so many real applications. And in this specific case, with ultra fast laser, pico and femtosecond, we can really address a lot of issue on the laser treatment of home appliances. So I would say I'm really waiting now to see what is coming in the next month or years, not too much. Which is your opinion? Maybe we can just make final comments from Rahul and from Johan, and eventually also from Anders, if he's still connected.
Yeah, from my side, of course, in the last years, there were a lot of differences and on the using of those technologies, because there was not before. I speak from the user point of view, because finally we are using machines to texturize mold or parts. There was not a machine able to move in the 5 axes in the space a femtosecond laser. So the limitations were on flat. Then with this machine appeared, a lot of new possibilities appeared, because now you are not just limited to flat parts or flat molds. Of course, most of the molds are on 3D shape because the products are 3D shape. No, in that case, as far as I know, one big limitation is that size and weight of the workpiece was limited because the machines were not very big. Of course, there were not before fiber for femtosecond laser, so it becomes more difficult to create a big machine, for example. Nowadays, the machines are becoming bigger with possibility to engrave more heavy workpieces or inserts. We work a lot for inserts that must be done specifically for our machine with the limitations of weight and so on. So the technology is evolving. We're going to have in few months bigger machine for much heavy parts. So it will be next step. So now the limitations will be not as in terms of size and weight, but some others, no. But yeah, this technology is evolving year by year, and we are living that right now in this moment.
Okay. Johan, what is your perspective?
When I started working in femtosecond lasers around 10 years ago, we had just, let's say, 1 to 5 watts mean powers with few kilohertz repetition rates lasers. And now we can have hundreds of watts, and in the LAMpAS project also 1.5 kilowatt lasers. So we clearly see the evolution of the lasers for industrial applications, because we want lasers to be faster and faster to face the market requirements. And we can also have now in femtosecond solutions infrared lasers, green lasers, UV lasers. So we have all the panel that is necessary to work on all kinds of applications. So this is a very interesting part. And I think that now the lasers are ready for industrial applications. The main problem now is how to use such high energy, high powers. And now we have to work on what we call beam engineering. It means that we have to know how to handle the energy, what kind of optics do we use? Do we use beam splitters? Do we use dynamic systems? And all of these systems are currently being developed in different kind of projects. And I think that, well, it's moving forwards, and we are at the beginning of using femtosecond lasers in the industrial, but generally speaking. And also it comes just in time when compared to the environmental issues. Femtoseconds are ready, and also we want to avoid chemicals. So we have a solution that is already available and which was clearly developed for decades. And so that's it. I think that the perspectives are quite good. We still have some research and developments to be done to be able to handle all of this energy, but this is very good perspectives for our field.
Yeah. I fully agree on your opinion, and I think it's also important that this is I share completely your point of view, and I can confirm, because in June at LASIS, EPIC, we will have a workshop, and the topic of the workshop is beam shaping, because now it's really important how you manipulate. I would say the laser, we have all the horsepower that we need in the engine. Now we need to understand how to bring into the tires to have the full speed. I don't know if Anders is connected and he would like to comment. Anders?
Yeah, so from the perspective of an end user, so we have been working quite a lot of years for following laser technology for surface structuration. Of course, in the case of in mold microstructuration, it's easier. The cycle time is not so critical because you need to treat the molds once. And we have several applications out there already. In the case of metal, now with LAMPAS, we are seeing, Antonio and John, you mentioned this now, the power of the lasers will not be a problem anymore. We are talking about more than 1 kilowatt, 1 picosecond laser, but we need to control all this power. And this is something also that LAMPAS could bring with the control loop, with the polygon scanning head and everything. So for us now, it's the case that we are really looking close to this technology, because we think that it might be close to industrialization, let's say in serious production for us. So it's very, very promising.
Okay, so I think that we can close now with the final words of Ander from BSH. This is a very interesting webinar on laser structuring of surfaces for home appliances. I would like to thank again, first of all, the three speakers. So Raúl Garcia from MicroReleus, Johan Di Maio from MANUTECH, and Anders Villalte from BSH. And very important, I will remind also the key results that we obtained through the EU money that founded the project LAMpAS. So this is a really extremely useful results and really ready to be used quite soon. So now I will say hello to all the participants, and for all who would like to remain a little more, we can chat really in a free mode among us for any other curiosity or things that we prefer to not share in the public. So thank you so much and have a nice evening to everybody.
Thank you.